Very much. Okay, now we're good to go. Please give a very, very warm science beers welcome to Professor Steve Brusatte, everybody.
Thank you.
You're welcome to ask questions on the way, by the way. All right.
All right.
Are you turned on?
Well, that's I'm going to answer that carefully. Am I turned on now?
Yeah, that's you.
All right. Well, thank you, Michael. Thank you, Claudia, for your opening act here. Wonderful. Really good. And if anybody saw the little toddler in the back, that was my son, Anthony. So don't judge us. He was here for a little bit. He was here to hear Claudia's music, which he loved. He had to get back to the hotel. But just in case you were judging, the parents bringing their 3-year-old to a beer event. If we knew there were smoothies, he would have stayed longer. All right. So how is the beer, by the way? I've just been drinking water because I want to make sure I'm on form. So is it good? You're good? All right, I'll try the beer a little bit later. And just before we start, condolences on the football score, by the way. We were watching and rooting for Denmark. We're kind of a mixed, household with England and America. And so yesterday's match was, well, it ended, I guess, the best possible way for us. Scotland never qualified recently, so, we don't root for Scots. Anyway, let's talk dinosaurs. That's why we're here, right? So I'm going to talk about dinosaurs and a little bit about mammals today. So I am Steve. Thanks, Michael, for the invitation and for the introduction. I'm really pleased that you heard that interview randomly on the radio driving around Belfast. It's good to know those things have such wide reach when we do these kind of things. So I'm based in Scotland at the University of Edinburgh. I'm sure you can tell, by my accent, I grew up a long way from Edinburgh. I grew up around the Chicago area back in America, but I made a career out of digging up dinosaurs, which is pretty cool, I think. I'm one of those lucky people that gets to do paleontology for my job, and I get to do it at an amazing university, a university that goes back to the 1500s and where the modern science of geology started. I know there's no geologists here, but we have some great biology in Edinburgh too. Edinburgh is where Darwin flunked out of medical school. So anyway, so that's what I do. That's where I am. We have a great paleontology research group in Edinburgh, and I've been there about 10 years. It's been a real privilege to be there. I also do a lot of public engagement and science writing and science communication, and I wrote a book about dinosaurs a few years ago, and I wrote one about mammals this year, which I'm told are available at the university bookshop here. If anybody is so wowed and riveted by this talk that you must go read the book, you can find them there. There's a few copies if you want to see just hoisting up the projector. They're really they're really good, especially the mammal one. It's like a big brick because it's only in hardcover, so if you want to take a look, just maybe wait till the talk is done. Anyway, all right, enough of the bullshit. Let's talk about dinosaurs. Okay, what I want to do is tell you in fairly rapid fire format, because we don't have a huge amount of time, in an hour or so with the break. I want to tell you the story of dinosaurs and also the story of mammals, how mammals took over from the dinosaurs. So it's about 250 million years of evolution. So instead of waffling, I'm just going to jump right into it. And we will start the story back when the world looked like this. This was the time, it was kind of called the Permian period of Earth history, about 250 million years ago. All of the land was gathered together as one. This was the age of the supercontinent, Pangea, and it stretched from North Pole to South Pole, surrounded by one giant global ocean. And much of that supercontinent was desert. It was a harsh desert, a tough place to live, but there were many plants and animals adapted to that world, including many early relatives and ancestors of mammals. But then something happened, something unexpected and something catastrophic. These enormous volcanoes started to erupt in what is now Russia. And it's always Russia, isn't it? It's Russia today, and it was Russia 250 million years ago. The worst mass extinction ever happened. This was the closest life ever came to dying out because those volcanoes, they were not normal volcanoes like we're used to. It's not like Mount Pinatubo, blowing its top one day, or the Hawaiian volcanoes spewing out a little bit of lava. These were giant, Grand Canyon-sized fissures in the earth that just released tsunamis of lava for over 1 million years. And that lava covered a land area like 3 times the size of Europe today. So it was absolutely horrific for anything living in that area. But the big problem was when that lava percolated up through the earth, it burned through the crust, and it released a lot of carbon dioxide and a lot of methane as well. Very powerful greenhouse gases, as we know today, causing global warming. Well, this was global warming to the extreme. And about 95% of all species died out. So only about 5% of stuff survived. Absolutely horrific, this extinction. And again, the closest life has ever come to totally being extinguished ever since the first little bacteria evolved about 4 billion years ago. But about 5% of things did make it through. There were survivors. Some plucky little things had what it took to make it through. And when I was a student, I was very interested in what happened with this extinction, and especially with the story of what lived, what died, how quickly things recovered, how a new world was made in the aftermath of that extinction, which was a new period of time that's called the Triassic period. And so I found myself spending a lot of time in Poland because there's some amazing fossils in Poland. Now, maybe Poland doesn't fit the stereotype if you see these television shows about dinosaurs or films about dinosaurs. People digging up dinosaurs. Usually it's, some Indiana Jones looking guy out in the desert, brushing sand off the bones, sweat, coursing off of his brow. That can happen. There are people like that dig up dinosaurs, but really all kinds of people look for dinosaurs, and you can find dinosaurs and other fossils really anywhere where there's rock of the right age, the age that dinosaurs lived, and rock of the right type. Rock, mud, stone, sandstone, the kind of stuff that was formed in ancient rivers, ancient lakes, the places where dinosaurs lived. And Poland's really good for this because there's all these quarries where they mine clay for bricks, and there's layer after layer of clay in those quarries. And you can read those like the pages in a book. And those layers of clay have fossils inside of them, and those layers of clay span that mass extinction. So you can see what lived and what died and how things recovered. And so my buddy Gregor Scher, he started collecting fossils from these rocks back when he was a teenager growing up in central Poland. Now, he has found some bones and some skeletons, but most of the fossils that we find in Poland are these kind of things. They are what we call trace fossils. They are not bones or teeth or skeletons. They're not parts of an animal, but they're records of an animal going about its everyday life. In this case, footprints and handprints, the little marks that these creatures made as they were running through the mud. And what we have here is a handprint to the left and a footprint to the right. They're kind of overlapping each other. They're very small. They're just a few centimeters long, just about the size of a paw print from your cat. And they were made by an animal racing across the mud about 250 million years ago, within 1 million years of that mass extinction. No more than 1 million years after those volcanoes erupted. Now, the animal that made these tracks looks something like this. I think a pretty weird looking thing, to be honest. This tiny little body, long, stilty arms and legs, kind of like one of those little Italian greyhound dogs. If you've ever seen one of those, really awkward creature, but clearly it could run very fast. This was an animal that was built for speed. Now, this thing was a reptile. And it was a type of reptile, again, it was about the size of a cat. You could hold it in your arms. And what's special about this reptile, living so soon after the extinction, is that it is a type of reptile we call a dinosauromorph, and that's just a fancy name for the closest cousins of dinosaurs. What you're looking at here is essentially the ancestor of dinosaurs. This is where dinosaurs got their start. And it goes without saying, but nothing about this animal looks like a T-Rex or a Brachiosaurus. It doesn't look like anything from Jurassic Park or Jurassic World, those dinosaurs that are so majestic that capture our imagination. This is a tiny little reptile that was scurrying around about 250 million years ago. But it was from these humble origins, these small reptiles trying to survive after this great extinction, that dinosaurs got their start. Now, it took these small, humble little reptiles quite a long time to evolve into anything that we would recognize as a big, scary, dominant dinosaur. Because for most of the Triassic period, there were dinosaurs there living on the supercontinent. After the extinction, these dinosaurs were diversifying, they were spreading around, but they were not the dominant animals. They were not at the top of the food chain. None of them got to be very big. It was other animals during most of the Triassic period that ruled the world. And we found fossils of some of these other animals in Portugal, down in the Algarve, a place where maybe some of you have been on holiday. Great place, to beautiful beaches, great food, great wine, all that. But you go about 20 miles, inland from the beaches, and you get into these scablands that are molded out of these red rocks, these hills with this rusty red rock. That's Triassic Age rock. It's bursting with fossils. We went there because we wanted to find dinosaurs from the Triassic period to help us understand the origin of dinosaurs, but we've yet to find a dinosaur there. And that's not because they didn't live there. They probably did. It's just they were so rare. They were so uninspiring and so unimportant at that time that they just didn't leave a lot of fossils. There weren't many of them around, but there's other animals that left tons of fossils in Portugal, and there are these kind of things. Hideous, hideous monsters. Amphibians, basically salamanders, the size of a small car. So imagine a salamander the size of a car. Imagine thousands of them living together in rivers and lakes. That is what the world was like in the Triassic when these first dinosaurs were getting their start. We have a bone bed of these things in Portugal. There looks to be hundreds of skeletons there. We've only removed a few of them because we can't dig them all out. But it's these things, which seem like something out of a fantasy world, that ruled the rivers and the lakes in the Triassic. If you were one of those tiny little dinosaurs, you would have stayed far away from the water because these things would have been there lurking. But dry land was no better during the Triassic period because on land, it was the age of crocodiles. Now today, we're familiar with crocodiles and alligators. They're plenty scary. You don't want to run into one. You hear all these stories of people, usually guys in Florida, doing stupid stuff. After a few too many, rolling out of the trailer, into the canal, whatever. You don't want to run into an alligator or a crocodile, but they're not particularly major players in the world today. There's only about 25 species. They all live in the tropics or the subtropics. They all kind of do the same thing. They can swim, they can waddle onto the land. They all kind of look the same. But back in the Triassic, there were all kinds of crocs and close cousins. There were crocs and their cousins that were nearly as long as buses. There were some that were covered in armor, spikes all over their bodies. There were others that had sails on their backs. There were others that lost all of their teeth and had beaks, if you can imagine something as ridiculous as a crocodile with a beak. There were some that only walked on their hind legs, and I could go on, but there was this incredible diversity of crocodiles and their close cousins. They ruled the land during the Triassic. There were more of them than dinosaurs. They were bigger than the dinosaurs. They had a greater diversity of diets and behaviors and ways of moving than the dinosaurs did. So really, for the entire Triassic period, from the time those first little dinosaur ancestors were making their footprints in Poland, for the next 50 million years till the end of the Triassic, there were dinosaurs. They were diversifying, but they were not particularly important. They were second-rate characters. They were the B-list or C-list actors, the bit characters. But we all know that dinosaurs would go on to glory, to grandeur. So what happened? Well, about 200 million years ago, the supercontinent started to break apart. And of course it did. Of course it did. That's why we have separate continents today. And so now the dividing line is marked by the Atlantic Ocean. It's the continents on both sides that came apart. That's why South America and Africa fit together like puzzle pieces. They were once connected. They moved apart. The Atlantic Ocean fills that gap. Same with North America and Europe. But before water rushed into those cracks, the Earth bled lava. And for about 600,000 years, it was another time of enormous, immense volcanoes. Not quite as bad as those Russian ones 50 million years earlier, because nothing's ever as bad as that. But these ones, they didn't erupt for quite as long, only 600,000 years. And they didn't quite release so much lava, but still, it was enough to do the same thing. Released a lot of carbon dioxide, a lot of methane, to lead to another global warming spike, and again this led to a mass extinction. Now, the victims of this extinction were things like the giant salamanders and most of the crocs. Almost all of that diversity of crocs disappeared, leaving just a few species, the ancestors of today's crocs. Whereas dinosaurs were the great success story. They were the survivors of this extinction. They made it through. Almost all the groups of dinosaurs that were there in the Triassic period made it through. They endured. They survived. They had what it took. And it's unsatisfying to stand in front of you and tell you this story without a reason as to why. We don't know why. We don't know what the secret to the dinosaurs' success was at that time. There's plenty of ideas. Maybe dinosaurs grew faster. Maybe they were warm-blooded and their metabolism helped, get them through the extinction. Maybe they were covered in feathers and that helped, survive the changes in temperature. Maybe they could run better than the other animals. There's all kinds of theories, but it's very hard to test those theories. And we don't have a solid answer. I think it's the biggest remaining mystery about dinosaurs. And there are plenty of mysteries about dinosaurs. There's still a lot of things we don't know. And I think this is the biggest one. And I do think some brilliant young paleontologists will figure it out one day. But for now, we don't have a good answer. We don't know why it happened, but we do know what happened. And that is that this extinction decimated the competitors of dinosaurs, whereas dinosaurs were spared. And then, as the extinction abated and the Triassic period turned into the next interval of time, the Jurassic period, nothing would ever be the same, because the Jurassic period is the time when dinosaurs properly spread around the world, grew to huge sizes, became dominant. They became the fantastic, inspiring, incredible animals, the things that we make movies about. There's a reason it's called Jurassic Park, not Triassic Park. If it was Triassic Park, it would be a film about slimy giant salamanders and weird crocodiles. Maybe a good film. I don't know what the soundtrack would be. It would be something really creepy and weird, not something majestic. So the Jurassic period is when the dinosaurs we all know and love, the big ones, the ones with long necks that grew to be the size of airplanes, the meat eaters that grew to be bigger than buses, the ones with horns and spikes and frills and duckbills and plates on their backs, and all of those things that just cry out dinosaurs in the Jurassic period, that dinosaurs became this way. And I think that's an amazing story, that it took like 50 million years for dinosaurs to become dominant. They had to wait their turn. And it was only those two extinctions that together enabled dinosaurs to take over the world. But once dinosaurs started to spread around and diversify in the Jurassic, they became dominant. We know now of about 2,000 different species of dinosaurs. That's what's been discovered. But there were surely many more. If you just think about how many birds there are today, there's about 14 or 15,000 species of birds today. Why that's relevant, I'll get to. But the point is that that's just today. Now, dinosaurs lived for like 150 million years, so just think about how many species there must have been. So there's still a lot more to be found. But we are finding more dinosaurs than ever before. Right now is the most exciting time in the history of the field. People are finding more dinosaurs in more places than they ever have. And somewhere around the world, somebody's finding a totally new species of dinosaur on average once every single week. So that's 50-some new species every single year. That means that's like hundreds of new species since I wrote that book. It's like nearly 1,000 species since I started my PhD, which I don't think was that long ago. But the point is, there's a lot of dinosaurs being found, and they're being found all over the world. Again, anywhere where there's rocks of the right age, so Triassic, Jurassic, or Cretaceous age rocks, and the right type. Rocks formed, rivers, lakes, on land, the places dinosaurs lived, you could potentially find a dinosaur. And we're finding so many new ones because there's more people than ever before looking for dinosaurs, especially young people. And it's not just, the little boys growing up in America like me or in Western Europe here that used to go into paleontology. It's now a much more diverse field, and you have young people all over the world, especially in places like China, Brazil, and Argentina, and Mongolia, and South Africa, these enormous countries that have such a wealth of fossils. They are going out, these young scientists, and finding their own fossils. And we are finding dinosaurs in so many places these days, we're even finding them in Scotland. And I think, to me, I never knew I would end up in Scotland. How can you ever predict the course of your life? It's been wonderful. But I never would have thought I would have ended up in Scotland. Even when I started studying paleontology, I never would have thought. I thought, Scotland, dinosaurs? Not really a thing. In fact, it was only in the 1980s that I later learned that the first dinosaur fossil was found in Scotland. It was a single footprint that was in a block of rock that had fallen off a cliff. And so, really, it's been less than 40 years since people have even known there are dinosaurs in Scotland. But we're finding more of them because we're looking a lot more. And there's really one place in Scotland where you can find dinosaurs. There's a few bits and pieces in other places, but almost all of the good fossils come from this place, and this is, to me, I think the most beautiful places in the world, one of my favorite places to go, absolutely enchanting place. Maybe some of you have been. Does anybody know where this might be? Has anybody ever been to the Isle of Skye? Yeah, I see Danish camper vans out there quite a bit when we're out doing field work. Many more German and Dutch ones. Those are the ones you got to avoid. It's like, drive on the left, come on. Isle of Skye, it's awesome. It's awesome. And if any of you ever get the chance to go. It's a great landscape. There's a reason so many Hollywood blockbusters have been filmed there just because of the landscape. You look at a scene like this. Those rocks, some of those rocks, along the coast especially, are Jurassic age rocks. So a lot of these cliffs and crags and other landforms, they're carved out of 170 million year old Jurassic rocks. Rocks a few tens of millions of years after that extinction when the supercontinent broke apart that ushered in the age of dinosaur dominance. So these rocks in Scotland record really part of the first wave of dinosaurs that had truly established themselves as these global, enormous, dominant animals. Now, every year we go out to Skye, sometimes a few times a year. I take my students out to Skye. My students always find the best fossils. I wish I could say I find the best stuff, but it's no exaggeration. It's the students, I don't know what it is, but they find the best fossils. I think because they're really motivated. And this is a prime example of that. This is Amelia there in the middle, who came out with us a few years back, and what she's pointing to, this is soon after she saw some little teeth sticking out of the rock on this tidal zone rock, and that turned out to be part of the jaw that connected to a head, which connected to a body, and that body was about 2.5 meters wide with a wing on each side. And it's a pterodactyl, a pterosaur, which is amazing. Nobody ever found anything like that in Scotland before. And in fact, in Britain, nobody had found anything like that since the days of Mary Anning. If any of you have ever heard of Mary Anning, who was maybe the greatest fossil collector of all time, who lived down on the south coast of England in the early 1800s, and of course never got the credit she deserved at that time as a young girl growing up in poverty. But she had an incredible eye for fossils, found a lot of pterosaurs. Then basically people found only bits and pieces of these things for over 200 years in Britain until Amelia found this one, which is amazing. And so earlier this year we unveiled it and we announced it. We gave it a name. We gave it a Scottish Gaelic name. We called it Yarkskianach, which means winged reptile, basically. I would love to say more about it, except pterosaurs are not dinosaurs. You might think they are. You often see them in dinosaur films and in dinosaur toy sets and so on, but they're actually cousins of dinosaurs, so I won't say any more about them. Anyway, we take our students out. Our students find great stuff. This is Moji. She came from Nigeria to do our master's course. We have a one-year master's in paleontology. And Moji actually studied fish fossils. So she's using this, this angle grinder to cut these little fish bones out of the rock. The rock is really hard. You have to cut fossils out. You can't use hammers and chisels and put the plaster jackets around it like maybe you've seen on TV. The rock is just too hard. Now, if you're looking for little fish bones, you can use an angle grinder. If you're looking for dinosaur bones, you need bigger tools. And this is Doogie Ross, our dear friend who grew up on the Isle of Skye. Actually, he's a native Gaelic speaker. He's one of the few people remaining who has Gaelic as his first language. When he was a teenager, he started collecting artifacts on Skye, and he established his own museum. He's the only person that I know who's built his own museum. And by that I mean he literally built it. He found the ruins of a 19th century schoolhouse, a one-room schoolhouse. He rebuilt it, and he put his collection in there of archaeological artifacts and fossils. So he's an incredible guy, a dear friend of ours. We work with him very closely. Thankfully, he is a builder by trade in addition to being a crofter. So he owns a parcel of land and he raises sheep and he grows crops and so on in the traditional Scottish Highlands way. But he's also a builder. That means he has diamond tip saws. That means he knows how to use them. And so there he is cutting a dinosaur bone out of the rock. Anyway, I want to tell you one story about the Isle of Skye, about at least until Amelia found that pterosaur, which I know I said I wouldn't talk about again, but hey, until she found that pterosaur, what I think our neatest discovery was. And this was a discovery we made in this part of the island, the far northeastern corner of the island, a place called Duntullum. I'm standing up on a hill in the shadows of the ruins of a 14th century castle. And that very Outlander kind of vibes there. I'm taking this photo. You can see the sky is blue, which is a weird thing for the Isle of Skye, where it rains all the time. And it's misty and it's windy and often the weather's really miserable. I think it makes Danish weather seem downright balmy on the Isle of Skye. But you might say, why am I standing up on this hill taking a photo when the sky is blue? Well, the problem is it's high tide. You can see the waves are lapping up against the beach. So we have to wait until low tide to collect our fossils. When the tide goes down, that beach turns into a rock platform that juts about 100 meters out into the very cold waters there in the North Sea. Now, we went to this place because a geologist friend of mine found a tiny little jawbone of a crocodile and showed it to me, and I thought, wow, that's amazing. Okay, maybe we can find a skeleton of this crocodile. Maybe it'll even be a dinosaur. And so we went there, we spent all day on our hands and knees, like really on our hands and knees, just scrutinizing that tidal zone. And we found nothing. We found nothing other than some shark teeth. It was a really discouraging day. But in reality, that's how a lot of paleontology is. Just don't go out and find dinosaurs, every day you go looking. So we were pretty despondent. We went back, we started to walk back to our vehicles as the sun was starting to go down. And as we did so, we started to look at these tidal pools. These are these, holes in the rock full of seaweed and algae, and there's little hermit crabs in there, and barnacles and limpets, and the normal stuff on the Scottish coast. But as we were looking at these things, we started to see that, wait a minute, there were a lot of these things. There were like over 100 of these little tidal pools. And they were all about the same size and shape, and there seemed to be a bit of a pattern to them. Kind of see where this is going. There's a bit of a zigzagging pattern. You can see a little left-right thing going on. That's weird for tidal pools. Then we looked at these. Some of them we could see from the side, and we could see they were actually impressed into the rock. So they had to have been formed by something stamping into that rock before the rock was rock, back when it was just wet sand, before it had hardened. So they couldn't just be erosion from the tides. And then some of these things were filled with a harder rock that stood out like a cast, and we could see little bits sticking out. You can see 1, 2, 3, 4 of those on top. And then others you could see very beautifully were paired together. There was a bigger horseshoe-shaped one and a smaller crescent-shaped one in front of it. And these things were truly big. Each one was about the size of a car tire. This is one of the biggest ones there with the lens cap for scale. Big things. So after a couple minutes, it dawned on us that, hey, this was actually a really good day. We had found fossils, just not the little crocodile bones we were hoping to find, but we found something much bigger and much different. And these are not bones or skeletons, but they are trace fossils. They are footprints and handprints, the marks that animals left behind, but so much bigger than those ones in Poland. Why? Because we're now in the Jurassic. Dinosaurs have now become ascendant. They've grown to huge sizes. And there's really only one type of animal that's ever lived in the entire history of the world that every time its hand or foot touched the ground, it would leave a hole the size of a car tire. And that's one of these dinosaurs, the great long-necked dinosaurs, the ones like Claudia's favorite, Brachiosaurus, and many, many, many other species. Long necks, tiny heads, big pot bellies, arms and legs that look like Greek columns, the very largest animals that have ever lived on land in the history of the Earth. Some of them that lived in the Cretaceous, the next interval of time, got to be heavier than Boeing 737 airplanes, which is remarkable. These were animals that hatched from little eggs and had to grow to that size. It's an absolute feat of biology. But what we're seeing, these ones that left their footprints and handprints in Scotland, were merely the size of 3 elephants put together. But they were some of the first truly giant dinosaurs that ever lived. Now, the more we look on the Isle of Skye, the more we find. Many of my students are doing this work. This is Paige, and she came from America to do a master's with us, stayed on to do a PhD. Paige has an engineering background in addition to a geology background, so she's very good at doing things like using drones and even building some of her own photo rigs to capture these footprints and handprints in exquisite detail. And that shows us what they actually look like across the entire site. We can see individual trackways, we can measure the spacing, that tells us how fast the dinosaurs were moving. We can tell from the rock what kind of environments they lived in, and what we are seeing, the more we find, is there's actually quite a lot of dinosaurs that left their footprints on the Isle of Skye in the Jurassic period. There's the long-necked ones, there's stegosaurs, the ones with plates on their backs, there's early relatives of duck-billed dinosaurs, there are meat-eating dinosaurs, and probably many more. And we are starting to find bones of some of these animals too. And this is how we imagine Scotland about 170 million years ago. And what we see here in this image by John Hode, who's a great artist in Scotland, great at setting these prehistoric scenes, what John is envisioning here is there's been a storm, the winds start to clear, and these dinosaurs are going out, wading in the shallow water of these subtropical lagoons, going out looking for food. And there's the giant long-necked dinosaurs there. And in the front, in the foreground, there is a different type of dinosaur. A dinosaur that's only walking on his hind legs. A dinosaur that, if you could zoom in, would have a lot of sharp little teeth. A dinosaur that would have looked something like this. Now, this one is actually from China, but we can tell that it's very similar to the fossils that we have in Scotland, which are much more limited, but there's great skeletons from China. What you're seeing here is a meat-eating dinosaur we call a theropod dinosaur. This one's just about the size of one of us. It's about human size. And believe it or not, what you're looking at here is one of the very first tyrannosaurs. This thing is the ancestor of TRex. Now, maybe some of you saw that TRex exhibit in Copenhagen. Maybe some of you have seen T-Rexes in other museums. T-Rex is a lot bigger than a human. So, this is where T-Rex started. I will tell you that story and wrap up the rest of it after you guys get a beer or a smoothie or whatever. So, we'll take our intermission now, if that's good, and we'll come back to it in a bit. Thank you. All right. Okay, oops.
Turned on?
Yeah. Turned on now. There we go. All right. Okay, thanks for coming back. All right, so where did we leave off? T-Rex. All right, so this thing is basically the ancestor of T-Rex. Now, these things were living 170 some million years ago. T-Rex lived right at the end of the age of dinosaurs, about 66 million years ago. So there was a good 100 million years of evolution to turn these things into the blood-curdling monsters that we think of when we think of T-Rex. So the question is, really, how did tyrannosaurs become so big? They started small. They were actually small for a very long time, for many tens of millions of years, and then they supersized towards the end of the time of dinosaurs. How did that happen? Well, for a long time that was a mystery, but we have new fossils that help tell that story. And this is another example. This fossil, it's a new species called Timurlengia that we named a few years back. And it comes from Uzbekistan, of all places. So another example of how dinosaurs are being found all over the world. Now, Timurlengia is important because it's an intermediate tyrannosaur. It's between the oldest and smallest tyrannosaurs and the latest and biggest ones like T-Rex. Now, Timurlengia, it's about the size of a horse. So it's not super big, but it's bigger than the human-sized things tyrannosaurs started as. And it lived kind of earlier on in the Cretaceous period, that next interval of time after the Jurassic. What's important about Timurlengia is that its fossils hold some clues inside as to how tyrannosaurs were able to become so big and so dominant. And it's this fossil in particular, which I'm sure you will all agree looks like some formless blob of rock or something. I don't know what it looks like. You know, do the Rorschach test. What is this thing? Well, I assure you it is a fossil. I assure you it's part of a fossil skull. And what you're actually looking at is the back end of this tyrannosaur skull. The hole is where the spinal cord goes into the brain cavity. All right, it's not the most beautiful fossil, and it's broken and chipped and damaged and so on, but we can put it in a CAT scanner, and we did this in Edinburgh. And the x-rays of the CAT scanner allow us to see inside this fossil, just like a medical CAT scan. And then we can use those x-rays to build a three-dimensional model of the fossil and also what's inside. That's important because this allows us to see inside of fossils and to do things like build digital models of the brain and the ear and the sinuses and the nerves and the blood vessels and all these internal bits, the things that can actually tell us something about how smart these dinosaurs were, what their senses were like, aspects of their biology and their behavior. And so if we pull that out, what you're looking at there, that thing in the lower right, that is the back end of this tyrannosaur's brain. The blue bit is the brain. The thing that looks like a pretzel is the canals of the ear, of the inner ear. Those are the parts of the ear, and we have them too, that help control the sense of balance. And it's actually the fluid in those canals that when it changes density, when you drink too much, that can cause a hangover in part. So remember that tomorrow morning. Anyway, the bit sticking down from that pretzel, which kind of looks, I don't know, like an ice cream cone or something, that's the cochlea of the ear. That's the bit that hears sound. Now, why this is important is because that blue brain, for a reptilian creature the size of a horse, that's actually a really big brain for a reptile of that size. That tells us this tyrannosaur was really smart, really smarter than a lot of other dinosaurs. The ear, that cochlea, is really long, and we know from modern day animals that the longer the cochlea, the greater range of sounds you can hear. So this tyrannosaur could hear really well. So this tyrannosaur, still just the size of a horse, not at the top of the food chain. It was evolving bigger brains, keener intelligence, sharper senses, probably to help survive in a world where there were still many bigger dinosaurs. But then, in the Cretaceous period, a little bit later on, there was another extinction event. Not a mass extinction, not a huge one, but there was some climate and some environmental change, kind of around 90 to 100-ish million years ago or so. We don't know a lot about it. There's not a lot of fossils from that time. This is another big mystery. What happened? But it seems like there's evidence from the rocks that there was another global warming event and big changes in sea level. Whatever happened, it seems like that affected a lot of the big meat-eating dinosaurs of the day, and a lot of them went extinct, things like the allosaurs and a lot of the spinosaurs and other things. And that left an opening at the top of the food chain. And tyrannosaurs were able to endure that extinction, maybe because they had keener intelligence, sharper senses. And they moved in very quickly. And they assumed, they seized that role at the top of the food chain. And then they supersized their bodies and they became things like T-Rex, which really deserve all the hyperbole you can throw at them. A famous dinosaur, an iconic dinosaur, is the one that, that every 5-year-old says is their favorite dinosaur. It's my favorite dinosaur too. I know that maybe sounds kind of lame. And I hope maybe some of you are T-Rex fans. You should be. It's not lame. This is an incredible animal. This is a feat of evolution. I think one of the most amazing things that evolution has ever formed. This was an animal as big as a double-decker bus. It weighed 7 or 8 tons as an adult. It had a head the size of a bathtub. I could fit inside of its jaws. It had about 50 teeth. Each one was the size and shape of a banana. It crushed through the bones of its prey. We know that because there are the shattered bones of things like Triceratops and duck-billed dinosaurs that litter the fossil record. And they have bite marks that perfectly match the size and spacing of T-Rex teeth. But still, yet it had those pathetic little arms. No bigger than our arms. So you imagine a city bus with our arms. I mean, it's just... So T-Rex was fearsome and ferocious, but also quirky and weird. And so to me, it's the most amazing dinosaur. I love T-Rex, but it took a lot of time for evolution to craft T-Rex. And T-Rex was there right at the very end. And I'll get to that in just a moment. But as we're seeing, over time, tyrannosaurs got bigger. And they started the size of humans, they became the size of buses, they became the top predators. At the same time this was happening, another group of close relatives, another type of meat-eating dinosaur, did the opposite. They got smaller and smaller. And these were the raptor dinosaurs. Don't believe what you see in most of the films. This is what the real Velociraptor looked like. The real Velociraptor is not, sadly, what you see in Jurassic Park. Those raptors are far too big. The real Velociraptor was just about the size of a poodle, and by that I mean a miniature poodle, not one of those weird big poodles, but a miniature poodle. And the real Velociraptor wouldn't have been green, it wouldn't have been covered in scales, it would not have looked like a giant lizard or crocodile. It would have been covered in feathers, and it even had wings. Raptor dinosaurs as a whole looked a lot like birds. And that's because they were the ancestors of birds. Today's birds came from these dinosaurs. Now, the reason that you don't see this Velociraptor in Jurassic Park is because back in 1993, when Spielberg was making the film, based on Michael Crichton's book, nobody had ever found a fossil dinosaur with feathers on it. So although scientists by that time were pretty convinced that dinosaurs were the ancestors of birds, they couldn't quite prove it, but even more than that, you would never put a feather on a dinosaur in a film. Back in the early 90s, there was no proof of it. That'd be ridiculous, even for Hollywood standards. I mean, Spielberg couldn't have gotten away with it. So, they didn't put feathers on the dinosaurs, but by bad luck, a lot of things went right with Jurassic Park. Of course, it became a global iconic brand, but they had one stroke of bad luck, and that was that 3 years later, after the film came out, in northeastern China, in a place called Liaoning, this province that's tucked away far off the tourist trail, it shares a long border with North Korea, land of factories, rolling hills, a lot of farmland. It was in 1996, 3 years after the film came out, that some of the farmers in Liaoning started to find some unusual things when they started to break open the rocks out on some of their land. And these things were dinosaurs, dinosaur skeletons, beautifully preserved, covered in feathers. Many of them even had wings. I think these are the most incredible, most gorgeous fossils. I think these things look like they belong in art museums. They are just splendid in every way. They are by far the most important dinosaurs that have ever been found in my lifetime. And we now have over 1,000 fossils of these dinosaurs covered in feathers, along with many other things. The reason that their feathers are so well preserved is because during the Cretaceous period, when these things were living in China, they were living in these lush jungles, but in the distance there were some volcanoes. And those volcanoes would periodically erupt and spew out ash, and that ash sometimes would bury entire ecosystems, kind of like Pompeii when Mount Vesuvius erupted. And so in Pompeii, you get humans that were killed by the ash, and they were like locked in place, cooking breakfast or walking the dog or whatever. That's what these dinosaurs were like. They were like locked in place by these volcanic eruptions, and they didn't have time to decay. Predators didn't have time to eat them, or scavengers didn't have time to eat them. So the feathers turned to fossils. This is so rare. That's why it took until the mid-90s for anybody to find something like this. But these are hugely important fossils because, first of all, they were the final piece of proof that yes, birds did evolve from dinosaurs. Feathers are so complex. Birds are the only things around today that have feathers. When you find feathers on dinosaurs, in addition to all the other evidence that have been building up, this proves it. Birds evolved from dinosaurs. But these things also tell us how birds evolved from dinosaurs, how feathers evolved, how flying evolved. The first thing that these fossils from China tell us is that feathers were a normal thing for dinosaurs. Most dinosaurs, maybe even all dinosaurs, had some feathers. In China, there are meat-eating dinosaurs that have feathers. There are plant-eating dinosaurs. There are little dinosaurs that are just the size of pigeons up to the size of dogs. There is even a tyrannosaur from China covered in feathers, a tyrannosaur that was about 8 or 9 meters long, that would have weighed over a ton. Its body covered in feathers like some kind of big bird from hell. Crazy thing to think about. So if you map this out on the family tree of dinosaurs, the only explanation is that feathers must go down at least to the common ancestor of dinosaurs, maybe even further out. But these feathers are not necessarily the type of feathers we think of when we think of feathers today. They're these kind of feathers. So this is part of the tail of one of these tyrannosaurs. Those are two of the tail bones at the bottom. These things above that look like scratches in the rock, those are feathers. They're simple feathers. They're little strands. They look kind of like hair, and they're hollow inside. These are the kind of feathers that most dinosaurs had. And this is the type of feather that we can predict that the common ancestor of dinosaurs had. Now, of course, these dinosaurs couldn't fly with these feathers any more than any of us can fly with our hair, or whatever hair we have left, Just not possible. So feathers did not evolve for flying. Why did dinosaurs evolve feathers? Probably the same reason mammals evolved hair. To help keep warm, to control their body temperatures as part of evolving a higher metabolism. And so most dinosaurs would have had feathers like this. So really, for dinosaurs, these feathers were just like hair for mammals. All mammals have some type of hair. Some mammals have more hair than others. Even dolphins and whales have little whiskers. Hair is a normal thing for mammals. The common ancestor of mammals had hair. Feathers were normal for dinosaurs. These kind of feathers. However, one group of dinosaurs started to change those feathers. And those dinosaurs were the raptor dinosaurs. And as their bodies were getting smaller and smaller, their feathers became ever more densely packed on their bodies. They started to line up those feathers, especially on their arms. Those feathers got longer. They started to branch out. They changed from simple strands into things that looked like brushes. And you got some raptor dinosaurs that turned those feathers into quill pens. Flattened feathers that branch out, that attach to the arm to form a wing, just like in birds today. What you're looking at there, the arm at the bottom, the stuff sticking down, that's a fossil wing. But this is not a bird, this is a raptor dinosaur. And it's this raptor dinosaur. It's this beautiful fossil called Zhenwanlong that we gave it a name a few years ago. I was invited by my dear friends in China to help study this with them. It's about the size of a big dog, a Great Dane, let's say. And the there it is. There's its bones. Almost all the bones are preserved by that volcano. And there's feathers all over its body, and you can see it has wings sticking out of its arms. The way those feathers attach to the arms, how they line up on the forearm and the hand, how there's different layers of them, the orientation, the size. It's like a dead ringer for the wings of birds today. But it's not a bird, it's a raptor dinosaur. Why is that? Well, it's really convention. It's convention because we consider birds to be those animals that have wings, that when they flap those wings, they can generate lift and thrust, and they can keep themselves in the air. In other words, they can employ powered flight. Now, some birds have lost that, like ostriches and emus and so on, but their ancestor would have been able to fly. So it's really a matter of convention. We say that dividing line between, dinosaurs and birds is when a dinosaur could fly, basically. These things were just simply too big and their wings were too small that if it flapped those wings, it couldn't keep itself in the air. I think if you saw this animal alive, though, back in the Cretaceous period, you would just consider it some kind of weird bird. A deviant, completely grotesque bird with those huge claws on its feet and sharp teeth in its mouth and a long tail. A weird bird, but when you think about it, is that thing any weirder than an ostrich or an emu or a turkey or a cassowary? Probably not. You would consider it a bird, but again, we just don't call it a bird because it couldn't fly. But you could imagine evolution over a bit of time. Remember, these dinosaurs are getting smaller and smaller, their bodies are. Their feathers are getting more elaborate. Why is that? Well, it wasn't because of flying, because these things couldn't fly. But they had feathers that were getting more and more elaborate. Why is that? We think it was for display reasons. Animals today do so many things to attract mates, to intimidate rivals. And so we think that's why wings actually first evolved, as these display advertising billboards sticking out of the arms. But you can imagine then, as these dinosaurs were getting smaller and smaller, those billboards on their arms were getting bigger and bigger, that at some point a threshold would be crossed. Just the simple laws of physics. Those wings, once this dinosaur started to move around those advertising billboards on its arms, they would provide a little bit of lift, a little bit of thrust. This dinosaur started moving in the air. Natural selection could then fine-tune it into an ever better flyer. That's how we think, more or less, flight evolved in dinosaurs, basically by accident, repurposing feathers that originally evolved for insulation and metabolism that then were elaborated for display, repurposing those feathers into an airfoil. Really, this is a similar way to how the Wright brothers, when they built the first airplane, what did? They didn't invent something from scratch. They took some wings, they took wheels, they took propellers. Propellers were originally developed to power boats through water. They took those things and put them together in a new way, and that's really what evolution did with making a bird out of a dinosaur. Now, it's a weird thing to think about, I know, and people still try to argue with me that, okay, maybe birds evolved from dinosaurs, but we shouldn't call them dinosaurs. A bird is so different from a T-Rex or a Brachiosaurus, it's wrong to call it a dinosaur. And I always just respond by bringing up these things. What are these things? Well, they're bats. What's a bat? A mammal, right? I mean, nobody would disagree with that. It has hair, it feeds its babies milk, it has molar teeth, it has all the things mammals have. It's because bats evolved from other mammals. They're part of the mammal family tree. They're just a weird type of mammal that got small, evolved wings, and developed the ability to fly. And birds are the dinosaur equivalent of that. They're just a weird type of dinosaur that got small, evolved wings, and developed the ability to fly. But the difference is, imagine a world where every mammal's gone extinct except for bats. That's really what we're at with dinosaurs. Now, all dinosaurs went extinct except for birds. What it means is that technically dinosaurs are still with us. And there are over 14,000 species of dinosaurs alive today, from our majestic American bald eagle to these little bastards. And, we got a lot of these in Edinburgh, as you have here. And I think when you're out at the beach, you're along the water, you're having some chips, you're having some ice cream, one of these things dive bombs you, tries to take your food. I think in that moment, in the cunning and the feistiness and the nastiness, you can sense the inner Velociraptor in a seagull. And that's because these things are really dinosaurs, and Velociraptor really is one of their closest cousins. So dinosaurs do live on today, but only in the guise of birds. All the T-Rexes and the long-necked dinosaurs, the dinosaurs with horns and spikes and all those things, they died out 66 million years ago when the world looked like this. By this time, the continents had been moving around, but dinosaurs were flourishing. There were different species living on every individual continent. And really, dinosaurs were still in their heyday 66 million years ago when, let's say, one Saturday evening, this 10-kilometer wide rock fell out of the sky. This was an asteroid. It was moving through the cosmos like 10 times faster than a speeding bullet. A piece of space junk. It could have gone anywhere. But it just so happened to make a beeline for the Earth, and it smashed into what is now Mexico with the force of over 1 billion nuclear bombs put together, and it punched a hole in the Earth's crust. It actually went down into the mantle, and that hole now is a crater that's over 150 kilometers wide, mostly covered by the waters of the Gulf of Mexico now. But this unleashed chaos instantaneously, earthquakes, tsunamis, wildfires. Then all of the soot from the fires and the dirt and the grime from the collision went into the atmosphere, spread around the world, blocked out the sun. For several years, the Earth went dark and cold. It was a global nuclear winter. And plants didn't have sunlight to photosynthesize, nor did the phytoplankton in the oceans. Things that ate the plants, things that ate the phytoplankton, they didn't have food to eat. They died, and so on up the food chain. Ecosystems on land and in the ocean, they imploded like houses of cards. And it all happened probably pretty quickly. And dinosaurs were there. T-Rex itself was alive when the asteroid hit. Triceratops itself, duck-billed dinosaurs, like Edmontosaurus here, they would have witnessed the asteroid. They would have had to deal with the effects of that asteroid. I really think it was, without hyperbole, the single worst day in the history of the Earth. This was no normal day. This was the biggest asteroid that's hit the Earth in at least the last 500 million years. And everything changed at that moment. Dinosaurs had been ruling the world for, 150 some million years. They had survived. They'd outlasted their crocodile and giant salamander competitors from back in the Triassic. They became ascendant in the Jurassic. They spread around the world. They grew to sizes that would be unmatched by any animals that would ever live on land in the future. And then, while they were at the top of their game, one day this space rock changed it all. And so a lot of my research now is turning to what happened after the asteroid hit. How did the Earth recover? How did a new world emerge from the ashes of the dinosaurs? So I've spent a lot of time in New Mexico, out in the Badlands. Very different than collecting fossils in Scotland or in Poland. We're out in the Badlands, out in what's traditionally Navajo land. This is one of the best places in the world to find fossils of the last dinosaurs and fossils of those animals that survived the asteroid and took over from the dinosaurs. Every year, we have a big research project going on now in Edinburgh, funded by the European Union, which thankfully I got that in before you know what. But we're really trying to understand the extinction and the aftermath. And so we find a lot of cool fossils in New Mexico. And when we are working in the Cretaceous, we walk these rocks, and we kind of go layer by layer. And these rocks are just full of dinosaur bones. I mean, you cannot walk without stepping on the shattered, remnants of a femur of a sauropod or the head crest of a triceratops. I mean, these dinosaur bones are everywhere, eroding out everywhere. And then suddenly they just disappear. That's the asteroid. And then we start to find a lot of new fossils. And those new fossils look like this. They're clearly much smaller than the dinosaurs, but they're not piddly little things. And maybe, these things might look a little bit familiar, especially in the upper right-hand corner there. Those things are teeth, and these things are not dinosaur teeth. They're not the steak knife teeth of a T-Rex. These things look a lot like our teeth. They're molars and premolars. They're the characteristic teeth of mammals with all those complex cusps and ridges and valleys. All of these things here are mammals. So it was mammals that really took over from the dinosaurs. Now, there's a lot I could say about mammals, and I'm really just going to close the talk with a teaser. And if you're really into mammals, there's a new book that you can read that can tell you the whole story. But the first mammals evolved at the same time as the dinosaurs. The mammal origin story, the dinosaur origin story is the same. The aftermath of that terrible Russian extinction in the Triassic on the supercontinent of Pangea. But dinosaurs were destined for grandeur. Yes, it took them some time to outlast the crocs and the big salamanders, but when dinosaurs made it, they went huge. Mammals did the opposite. They stayed small. They stayed in the shadows. They couldn't really get big in a world where dinosaurs were becoming as big as jet airplanes. There wasn't the space for mammals to get big. So mammals had to learn to adapt. They had to learn to survive. They had to have persistence, and they did, and they became incredibly good at living underground, underfoot, living in the night. And for 150 million years, mammals lived with dinosaurs, but none of those mammals ever got bigger than a house cat. Then the asteroid hit. And within about 200,000 years or so of the asteroid, in New Mexico, we have mammals the size of pigs. Within a million or so years, mammals the size of cows. And then they would just keep getting bigger and bigger until things like whales got even bigger than any dinosaur ever got. Now, the secret for these mammals, it seems, first of all, we had ancestors, and I think we need to remember this. We had ancestors that endured that asteroid. We had ancestors that stared down that asteroid and got through that extinction. And they were able to do it because they were small, because they could hide easily, they could dig burrows, they could eat lots of different foods, they could grow really fast. That's probably what allowed our mammal ancestors to make it through when the dinosaurs couldn't. Most dinosaurs, other than birds, were big, they had very specialist diets, they couldn't really hide very easily, so they had a very bad hand of cards when the asteroid hit. But our little mammal ancestors, they had the winning hand of cards. But now, imagine you're one of these little mouse-sized mammals that's made it through the extinction. The asteroid's a distant memory. The nuclear winter is over. The plants are growing again. But there's no T-Rexes anymore. There's no Triceratopses anymore. There's abundant opportunity. And what did these mammals do? They got big. They got big really fast. And they filled those ecological roles that dinosaurs once filled. And the secret to getting big seems to be that most of these mammals were mammals like us. They're placental mammals. They're mammals that gave live birth to well-developed babies. In the world today, there's about 6,500 species of mammals. There's a few monotremes, like the platypus, that lay eggs. These are a totally ancient group of mammals that by crazy coincidence and dumb luck has survived to the present day. I mean, it's crazy. I mean, it's as weird as having like a surviving, Brachiosaurus or something. Honestly, they are so strange, but they hold on today. We should cherish them. We don't enough, I don't think. Then there's marsupials. There's some marsupials, nearly 400 species. The ones that give birth to tiny little babies they raise in pouches. Those are more common in Australia and South America. Australia is an island today. South America was an island for many tens of millions of years. And so marsupials really incubated in these places where they were able to reach. But the vast majority, like 95% of mammals today are placental mammals, like us. There's Anthony, about a year ago actually. My model for what a placental mammal is. And so it was placentals more than any other type of mammals that really took off after the extinction. They actually got so big so fast that we've just learned in this paper that my postdoc Ornella here led earlier this year. We published this paper in Science. That we did all these CAT scans of the brains of all these mammals over time, we actually found that these mammals, after the extinction, got so big so fast, their brains didn't keep up. And because it's relative brain size relative to body size, that's really the seat of intelligence, these mammals that were taking over from the dinosaurs actually were getting stupider. So it wasn't big brains that really helped them, but their bodies were getting so big. So this was such a weird finding that Ornella found. So they got big really fast. It was big body sizes more than anything that was their key. How did they get big fast? Well, we've just done a study. We published it a couple months ago. This is led by Greg Funston, who's another one of my postdocs. We published this in Nature, so it was a good year for Greg and Ornella. Greg was able to come up with some new techniques using histology of bones and teeth, making very thin cuts and looking under the microscope. You can see growth lines, including daily growth lines in these fossil teeth. The real big insight that Greg had was to use geochemical techniques. You can actually look at how the chemistry changes across those growth lines, and you can identify these spikes where there's a big change in zinc and a big change in barium. And you might say, who cares? Who cares? But we know from modern mammals today that when an animal is born, when a mammal is born, it has a big geochemical change. It's a big stress event. It's going from in the womb where it's nourished by a placenta out into the world. Then there's another big chemical change when that mammal is weaned off of breast milk. And so that means that Greg was able to find these same signals in these mammal teeth that are more than 60 million years old. We're able to tell that some of these first placental mammals, getting big, living soon after the asteroid, raised their babies in the womb for 7 months. We can tell that from the growth lines and the chemistry. We can tell that those babies drank milk for 1 to 2 months and then started to eat solid food. And then within a year, they started to make their own babies. So it was probably raising their young in the womb for so long, allowing those babies to get bigger and bigger while in the care of their mother, that was the secret to these mammals being able to get so big so fast after the asteroid. And that's culminated in, again, the more than 6,000 species of placental mammals today. Everything from tigers and horses to bats and elephants and whales and Muhammad Ali and all of us. And so we really are in a world of placental mammals. And again, this includes us, because in New Mexico, when we're looking for these fossils, a few million years after the asteroid, we start to see these tiny little teeth and some bones of the skeleton. And we can tell that these animals are about the size of a house cat. They had long gangly arms and legs, but they had long fingers and toes that they could use to grip the branches. These were really good climbers. These things were the very first primates. They were ancestors of ours, really direct ancestors of ours. They only got their opportunity because that asteroid knocked off the dinosaurs. And they were getting bigger, and they were raising their babies in their wombs for a long time. And this was the start of our story. So all this stuff is intertwined, the dinosaurs and us. I'm going to leave it there. I could go on forever, but there's a beer to be drunk and questions, I'm sure. I'm happy to take any questions here or downstairs, however we do it. But cheers, everybody. Skål.
Let's go. Who wants to ask the first question? Yes?
I was curious about, you said that the reason that we could grow, the mammals grew big very fast was because they were placental. That was a good strategy. Were the crustaceous and the Jurassic mammals not?
That's a great question. We don't know the answer yet, because there's not a lot of great fossils of the mammals from the Jurassic and the Cretaceous. There's some. They're all small. It's all very hard to study their teeth and to make those little thin cuts you need. We're hopeful that things like synchrotron scanning can help, but really we need to test how long those things were raising their babies in their wombs. So we don't know yet. We don't know if that style of raising your babies for a long time in the womb developed right after the extinction, or maybe it had developed before the extinction, but it hadn't yet allowed mammals to get big because there were still so many big dinosaurs. We just don't know. So Greg, is now off on another postdoc, and he's, hopefully very soon to be starting his own lab. He's looking into all of this stuff. He's got some big grant applications out, and I'm hoping he can get the funding for this, because you zoomed in on a big question now. So we found this for the first time in one of these mammals right after the extinction. Now let's go back and see when this evolved.
I was wondering if, like when you said that feathers, they developed as like display, if there's been like signs of sexual dimorphism in feathers and everything.
Yes, there is some. So there's also been studies of sexual dimorphism in dinosaurs when it comes to the skeletons, but it actually is really hard. It seems like dinosaurs did not clearly have dimorphic skeletons. It's not like the females are always bigger or the males are always bigger or whatever, at least that we can tell. But very few dinosaurs are known from enough fossils to have the statistical sample size you need. The same with feathers. But what we do know is that there's some early birds, true birds, real birds that could fly, that are found in those same rock units formed by the volcanoes. And that's because those volcanoes were erupting and burying these dinosaurs after some birds had evolved. Some of those birds have very different feathers, and there do seems to be two different types. Kind of a simpler type, and then one where there's very elaborate feathers on the tail. And those ones are probably the males, probably. So that's, I think, the best evidence we have. I think probably dinosaurs would have been dimorphic in their feather colors, like many birds are today. And we can tell the feather colors of dinosaurs, by the way. And you can thank Denmark for this, actually. There's a Danish scientist, a friend of mine, Jakob Winther's his name. Maybe some of you have heard of Jakob and his work. Jakob's on the faculty in Bristol now, but when Jakob was a student, when he was still a student, he wasn't actually studying dinosaurs, but he was studying fossil squid, and because that's what he's really into. And there was like this fossilized ink sac that was preserved. I know I'm going on a tangent, but it becomes relevant. But he kind of knew it was an ink sac, and it was kind of dark in color, and he looked at it microscopically, and he found these bits in there called melanosomes. These are the little organelles that hold pigment. And the ones in that black fossilized ink sac were the same types as in black colors today in feathers and skin and ink. So that led him to think, wait a minute, maybe you can actually get these pigment bubbles preserved in fossils more widely. He started to look at dinosaurs, dinosaur feathers. He found dinosaur feathers. And he started to find there was a huge variation in the colors that different dinosaurs had in their feathers. But so far, maybe only 10 dinosaurs, if that, have been studied, because you need really good feathers. So if we could study all dinosaurs, my guess would be that many of them would have had sexually dimorphic feather patterns and colors. So that's a prediction, and maybe somebody can test it in the future.
Over here.
There seems to be portrayed some kind of correlation between that the bigger the better, the more dangerous, the highly evolved the creature is. In botany, there's this astonishing field that within the popular family of the roses, which is quite common, there's apple trees and roses, of course, and strawberries, all with the same family. And one might think here that the apple trees are the bigger ones, so they would be highly evolved, but actually the strawberries, they have the capability of freezing below ground, so that is believed to be the evolved trait. Is there similar contradictions? Can you feel?
Yeah, I think all of these different dinosaurs were kind of highly adapted in their own ways. So I think we give a lot of attention to the really big ones, the T-Rexes and the Brachiosauruses, and for good reason. Those things really push the boundaries for how big things can become on land. But I don't think that makes the smaller dinosaurs any less important. And really, it was the smaller ones that turned their feathers into these elaborate structures that were the ones that evolved flight. And so, only 3 types of animals with bones have ever evolved powered flight, where they flap wings that can power them through the air, and that's pterosaurs, birds, and bats. So it's a very rare thing to do. Those smaller dinosaurs, although maybe, yeah, if you looked at one of them way back when, you'd say, oh, this thing isn't anywhere near as spectacular as a T-Rex. It isn't as evolved. But no, it is, and it was in its own way. And in fact, it's those dinosaurs that are the only ones that survive today.
Over here, Steve.
Yep.
Yeah. Hello. Thank you for your talk. I have a question. We talked about feathers, right? From the raptors to the current birds. How the beak came?
Oh, the beak. Yeah, good
because
question.
we have like the Triceratops has a beak,
Yeah.
but it's not related to what now the birds are. So how did that happen?
Yeah, so lots of animals have independently evolved beaks, whether it's a bird, Triceratops, turtles, there's lots of different things, even some of those weird crocodiles from the Triassic that I mentioned earlier on. So as far as how birds evolved their beaks, they came quite late because birds don't have teeth. Modern birds don't have teeth, but in the in the Cretaceous for sure, there were plenty of birds that did have teeth. And so you kind of see one group of birds evolving a beak structure in essence to replace the teeth. It's probably not that simple. But in general, birds developed beaks, lost their teeth. What's interesting is that when the asteroid hit, most birds died. There were birds still there. There were lots of different birds. And when the asteroid hit, there were birds that had teeth. There were birds that had big claws. There were birds with long tails. There was this whole menagerie of birds. And all of them died with the other dinosaurs. The only type of bird that survived, the only type of dinosaur that survived, were the advanced birds that had beaks and no teeth. And the thinking is, one of the leading ideas, is that beaks allowed those birds to eat seeds. And if you're living in a world where it's cold and dark for like 10 years, and there's no photosynthesis and the trees die and the forests collapse, seeds are one of the only things that would be out there to eat. Seeds stay in the soil for a long time. That's why the trees grew again when the sun came back down, because there were seeds still around. So having beaks may have been the key for those birds to survive. So whether they originally evolved those beaks in order to eat seeds, I don't know. But certainly in the Cretaceous, there were some birds evolving beaks, losing their teeth, and those are the only birds that persist today.
Over here.
If you had all the money in the world, you're still a young fella, you've got long time to go, with infinite time and infinite money, and Russia doesn't cause another mass extinction. What most outlandish theory would you like to have proved before you move on to the next world?
Oh, wow. Well, with paleontology, there's two sides to paleontology. There's the discovery side. We do go out and look for fossils, and there's no advanced technologies that help us with that. We walk around, we look to see what's sticking out of the rock, and that's it. And so it really is kind of like gold prospecting, or something like that, which means that you can't ever predict what you're going to find. And it's almost impossible to say, I'm going to go out and try to find this type of fossil. The other side of paleontology is the side of what we do with fossils when we bring them back to the lab. And that's when we can use lots of technologies, and whether it's CAT scanners or the geochemistry or whatever, to test particular ideas. If the question is if there's a single thing I could find, what I would love to find, or have somebody find, is a fossil ecosystem like that one in China, buried by volcanoes, so everything's preserved in such pristine condition. But not from the Cretaceous, but from the Triassic. Because if feathers go back to the common ancestor of dinosaurs, the Triassic ones were probably feathered too. And so if we could find a place that preserves dinosaurs in such exquisite detail, we could test that idea that the common ancestor of dinosaurs had feathers, that all dinosaurs had feathers, and we would see what those feathers looked like. And were any of those dinosaurs early on experimenting with gliding or maybe even flying? Does that go farther back than we think? So that would be the one thing I would love. The other thing would be a nice fossil bird from the Isle of Skye, because if we found one on the Isle of Skye, it would be the oldest bird in the world. So could it be? I don't know. So, yep.
Over here.
Alright, so maybe a silly question, but mostly rooted in that I love bees and look at a lot of bees and read about bees. I've read a book by Lars Chitka about the mind of a bee and how they have a lot of evidence of a lot of cognitive aspects of bees despite their small brain size. Based a lot on, even now they've shown that they actually do play just for shits and giggles. And I was just wondering, what they've shown is that even small brains can comprehend a lot of intelligence, as you might say, or cognitive abilities. So I was just wondering if you base the intelligence of the dinosaurs, you mentioned that early Pterosaur, if you base the intelligence on more than the size of the brain, or it's just the size of the brain, or how you do it. Thank you.
Yes, it's a very good question. I mean, when we talk about intelligence in dinosaurs, we're talking about it very crudely because we don't have fossil brains. We don't know, we don't have direct evidence of things like neuron counts or neuron density or these kind of things. All we have to go by is the space in the head where the brain once was. And we can use CAT scans to, to see inside the skull and build a digital model. And that can tell us the size and the shape of the brain. And then we can, look at the size in relation to the body. And it gives us very crude estimates of intelligence. And we do know from modern animals that brain size relative to body size, it does matter. A lot of aspects of intelligence do correlate with that. But of course, many, many things don't. For something as complicated as intelligence or cognition, relying only on the size of the brain is so limited. So we try to be, humble in that regard and try not to go too far beyond. Because yes, probably a lot of dinosaurs with smaller brains, maybe their brains were wired differently. Who knows what they were capable of. We are trying to do better with this, though, and we are trying to make links now between what we can see and what's called the endocast. That's the thing that we can make, the digital or physical cast of the brain cavity. It's called the endocast. Things that we can see on the endocast that might correlate with aspects of intelligence, behavior, cognition, neurobiology in animals today. We're at the very early stages of this, but I'm part of a team that's led by a cognitive biologist in Lund, not too far away, a guy named Matthias Osvath, who's one of the world experts in the field. He put together a team that also includes some great neurobiologists that have pioneered a lot of the work on counting neurons and studying neuron density. And then myself and another paleontologist named Larry Whitmer who study a lot of the brains endocasts of dinosaurs. We've come together, we have this team, we actually got funded through this big Swedish grant to Matthias. I don't know, maybe Sweden's flushed in money. It's certainly not like that in the UK, but it's exciting. For the first time, we actually have paleontologists who study dinosaurs and CAT scan dinosaur skulls working with real cognitive biologists and neurobiologists with like 6 years of funding to work together on this stuff. So we've just started. And I don't know what we're gonna find, but we are trying the best we can to see what anything that may record itself in the size or shape of that endocast in a dinosaur that we can correlate to real aspects of cognition and neurobiology. So wish us luck, and we'll see.
We're going to have to wrap it up real soon. There's a question over here.
Yeah, this is a great one to wrap on. You are an author right now, so probably the most silly question in the world. Are you drinking Unser Classic right now?
I can't possibly answer that.
No, he is, of course, drinking Onza 1859 because that was the year that Darwin's Origin of Species was published. Yes! Yeah. You're hanging around, Steve, yeah?
Yeah, I'll be here for a little bit. Yep,
Yeah, you got your karaoke
absolutely.
song sorted?
We will figure that out.
Thank you guys very much for coming along to the season finale of Science and Beers. We are going to have to get the party started. Yeah? So we're going to go downstairs. And we're going to sing some songs, drink some beers, and maybe have a little bit of a chin wag with Professor Steve Brusatte here. If you have any more burning questions. Does that sound like a plan? Yes?
All right.
I will say that because there's so many, we actually took all the chairs from downstairs. So if you want to hang around and you're sitting on one of these seats, just bring it downstairs with you. Yeah. This was the season finale. So Mark and Peter and Asta and Kenneth, the Science Beers volunteers, please come up on the stage here. This has wrapped up the whole season, 2 seasons this year. We hope to be back next year from March onwards. And thanks to these guys. Claudia Campagnol, come up the stage here. Get your shoes on, Claudia Campagnol, everybody, her album right now is out. Steve Brusatte, come on up here, please. Professor Steve Brusatte, all the way from Edinburgh, everybody. Thank you very much for coming. Cheers to science. Yes. See you downstairs in the karaoke stage.